My session, how SQL Server works and how to make your queries run faster. My objective today is to talk to an audience that typically uses SQL Server as a data source in their data science world, but doesn't really do much other than fire queries at it. So I've spoken to a couple of people at the front who said that this is perfect. We're going to look at how conceptually SQL Server works when you ask it to retrieve data for you. And then we're going to look at the most common causes of why queries run slowly and how you can make them run quickly. So hopefully, just to set everyone's expectations, that's my goal this evening. So my name's Gavin Payne, as Adam mentioned. I used to be a principal data architect at Coeo. I am now head of digital transformation, so I do evangelism and innovation in the commercial leadership team. The business I help lead, we're an analytics and data management consultancy. We provide consulting services, managed services, technical services, and we're focused on that Microsoft data platform. My contact details are at the bottom, so if anyone has any questions at the end, feel free to ask me, or do feel free to contact me afterwards. So our agenda is threefold, really. Just to reintroduce to people familiar with it and introduce newcomers to what SQL Server is. So a conversational level overview of what this product is. We'll look again at a conversational level as to how it works when we ask it to retrieve data, with the purpose of being able to understand why queries might work slowly and how we can then optimize queries. And then we'll wrap up by looking at some of the most common causes of queries taking a long time to run. And my objective, and I don't have a clock, is to try and do that in about 35 to 40 minutes. So as long as that chap keeps his wrist still, I'll be on time. All good so far? Everyone happy? Nobody that was expecting me to talk about sharks or wildlife? No, we're all good. So what is SQL Server? It's been my background in my career for the last couple of decades. It's Microsoft's enterprise data platform product. There's been 11 major versions in 27 years. So this is quite an established product in any industry of technology, never mind in Microsoft's armory. It's obviously had a lot of innovation over those 27 years. So whereas when it started, it was sort of something that ran on a big PC in the corner of the office, it now runs on some of the most powerful servers that you can buy and everything in between. So we've got that breadth of capability now. Originally, the product name SQL Server just referred to a database engine. So a transactional structured relational database engine that stored rows and columns in tables that we could run queries against. It's now a complete enterprise analytics product. So inside the box that you buy, you get SQL Server Analysis Services, which is their tabular and multidimensional cubing product. You get an ETL service, you get a reporting service, you get data quality services, you get master data management. There's about 16 products that competitors would sell as individual products that now come under this umbrella of SQL Server. So we sometimes confuse ourselves when we talk about we've got a database server that uses SQL Server. It might be 27 years old, but it's going through a lot of change at the moment to keep it relevant and modern. So as well as being at home on Windows, from later this year, it will also be at home on Linux. It's also available in a container format for both on-prem and cloud worlds, and there are also Cloud PaaS variants. So this has moved on a long way from just being that SQL Server.exe that runs on a Windows box in the data center to having lots of different cousins and brothers and sisters that sit under that SQL Server family. Most of them work in the same way that we're going to talk about tonight. So what I would ask you is, while we know that SQL Server has different features, different ways of working, we think conceptually about how the product has always worked and how we interact with it on a day-to-day basis. So now we know a bit more about what it is. What do people use it for? And this again starts us to think about when we work in that data science arena, if that's where you're from, or analytics or business intelligence. Why might organizations have a data source that uses SQL Server? So for the last couple of decades, it's been the mid to large marketplaces default option almost to be their transactional database engine. So for a lot, but not all, commercial third-party applications, CRM systems, ERP systems, SQL Server is increasingly the preferred option to store their data. It's also for developers that have come up through that Microsoft ecosystem. It's their preferred relational database engine to store the data that their applications create and use. So there's a couple of decades worth of deployments out there that are now storing data which increasingly businesses are asking analytics questions of. It also does have a role, the database engine, in that analytics family. So from about 2000 onwards, Microsoft started to create these analytics tools within the SQL Server box. And what we start to see now is that there are some very, very large enterprise data warehouses that run on the SQL Server database engine. There is in fact a multi-parallel processing variant of SQL Server that will happily scale your data warehouse into the petabyte range. When we work with those, we often find people use star schemas, dimensional modeling, the Kimball methodology. So again, these are approaches that the developers that create a data warehouse in the SQL Server world will reach to first. It may well be that's the same with other vendors, but this is definitely the case, and there are internal optimizations within the SQL Server database engine for data warehouses with star schema databases. The challenge is that SQL Server's capability for most of the 90s and 2000s was always bigger than the hardware it ran on. So companies like those that I help run, a lot of our work is actually right-sizing the platforms that these database servers run on. So while people for a long time have created data warehouses using SQL Server, it's common to find that they don't have the server platforms that give them the horsepower to perform as we'd expect. So a bit of a journey now as to how SQL Server actually works. So when we submit a select query to it, we're going to look now at actually just what happens under the hood. And the idea here is to help us understand what all the different moving parts are and start to consider where the bottlenecks might be and where the optimizations might come from, and some of the terminology that will help us with troubleshooting as we go through that journey. So SQL Server uses a variant of the ANSI SQL language called T-SQL. Transact SQL, it stood for many years ago. It's been abbreviated now. So users will write a T-SQL query in any tool that they want to that can connect to SQL Server. Most may use something like SQL Server Data Tools or SQL Server Management Studio. It could be Excel, it could be a Linux command line. But all SQL Server really sees is that T-SQL query that a user fires at it. That gets received by this first chunk of the engine, which is the relational engine. So the first thing that does is to actually just run a command parser through it to say, is that valid T-SQL? Has somebody just written junk, or is this valid? And the types of things that excludes is things like white space. So you can put as much formatting, carriage returns, spaces in your query, and SQL Server, when it gets to that stage, it ignores those and treats everything as a like-for-like, just raw text rather than formatted text. So the next thing the relational engine does is to send that query to the query optimizer. And that's one of the biggest black boxes of crown jewels Microsoft have for SQL Server. So this is really a library of all of the algebra that is used to turn a T-SQL query into actually a set of physical operations that the database server will then go and perform. So it's almost almost an interpreter. So it doesn't actually compile anything in a traditional executable way, but this is actually turning human readable T-SQL into SQL Server database engine readable commands. And that generates something called a query plan. So this is a very large XML document that essentially describes all of the physical operations that SQL Server in a moment will go on to perform to actually execute that T-SQL. And you can look at query plans. You can get graphical interpreters that we'll see at the moment, so you can visually see what that query plan looks like. The query plan also contains a lot of execution parameters, like how much memory the query is going to need, how many CPUs it should run on. So there's a lot of operational metrics in there, as well as commands about retrieving the data. So that query plan then gets passed to the storage engine. So this is really where SQL Server now starts to get data from physical files and pass it back up through the relational engine to the end user. So the first thing the storage engine does is know that there are some database files stored out on the operating system. So they commonly see them have the extensions of MDF for a data file or NDF, and LDF for the transaction log. So these are flat files stored out on the operating system that the storage engine knows about. So the first thing it does when it wants to retrieve data is it moves data pages from that physical MDF file into its data cache into memory. So the first thing that we see about SQL Server's behavior when we start to think about how it works, how it might run slowly, how we can tune it, is that SQL Server always copies data from disk into memory and then does something with it. So once that data is moved to the data cache, it then gets passed back up to the end user. So when we think about tuning our platforms, the biggest consideration, especially with analytics workloads to consider, is I might be retrieving 100 gig of data here, and I might only have a cache of 10 gig. So SQL Server literally does have to swap out that cache 10 times to satisfy that query. So what we immediately see now is SQL Server loves memory if we're starting to use large amounts of data, because all of the data that we retrieve goes through its buffer pool and out to the end user. The reason it does that is because the worst thing you could ever do in a SQL Server environment performance-wise is to run exactly the same query again and it not have any benefit of having just done it to try and reduce the impact of repeating that operation. So if your query just retrieves 8K of data and you've got 128 gig of memory, it may never need to go to disk for as long as that server is running, because that data is always in memory. And that's the goal of the database engine, is to reduce the number of physical I/O operations. So we're all comfortable just at a conversational level of what's happening there. But more importantly, that we've got query plans that we can look at, which are actually how SQL Server is physically performing these operations. And also the fact that that data cache is kept in memory. It can never be written to disk in normal operations. And data never goes straight from that data file to the user. So when we think about what we call an instance of the SQL Server database engine, it's basically everything in that black box, in that red box, that is running on the server. So that instance of SQL Server.exe will have data files on the operating system, but when we try to describe what is contained within that instance term, it's basically everything in that red box. So let's think about some of the challenges in the data science world. So what we've just described there about how SQL Server takes data from physical disk to memory to the user, that's what it does for every type of query it can ever process. So that could be for a high concurrency transactional system where the average amount of data that a query uses is 1.5K, or it could be for an analytics system where people run queries that process hundreds of gigabytes of data. So it is a good universal engine, but we immediately start to see that on its own, without some extra management, we're immediately going to start hitting performance bottlenecks. The biggest bottleneck in this area is the amount of server memory. So if we know that our working data set is 20 gig of data, and we've only got 8 gig of data in that server, it's going to run pretty slowly. If we've got 64 gig of memory, and we routinely only use 20 gig, it's probably never going to read from disk more than once for each data page, because once it's in memory, it never has to flush the cache. So where we have 20 gig of data and 64 gig of memory, that's very common in OLTP transactional systems. The inverse is very common in analytical systems, and that's why we have to tune the server platform to really cope with the fact that it's probably never going to have enough server memory. So if you have a 5 terabyte data warehouse, you're never going to have several terabytes of memory to cache that. What we have to do there is to work on the assumption that actually in those large data warehouse environments, the memory in the server is just a small little performance enabler. It's the performance of the physical storage that then becomes the bottleneck, and we tune that storage. The query optimizer, so that's what creates the query plans, that actually determines how much data is going to get read from disk to satisfy your query. So while you might think that you're going to write a really well-tuned piece of T-SQL, SQL Server may look at that and decide to do the stupidest thing when it comes to performance optimization when it physically implements that. It thinks it's doing the right thing, and its pre-programmed algebra will have a very good damn reason why it's doing that, but the reality is that tuning your query plans rather than tuning your queries can be where some of the biggest optimizations come from. How are we doing for time? Okay. So conceptually, let's look under the hood a bit more. How SQL Server works. So in normal database operations, everything SQL Server touches in the cache and on disk is an 8K data page. Of that 8K data page, you have a maximum storage of 80-60 bytes. And you can have data types that are both fixed width and variable width. So when we think about how SQL Server manages that 80-60 bytes, we start to see the physical layout of the record looking something like the bottom right-hand corner. So when we compare that to perhaps a big data structure, where we may have a much more human-readable record format in a text file, there's a lot of mechanics that happen under the hood for SQL Server to cope with the fact that it's got to store variable width columns, fixed width columns, some metadata about that row. There are gotchas, there are workarounds. You can store data in a column that's up to 2 gigabytes. So there are some very large data types. And they're known as off-row data types because essentially only store a physical pointer in that row, and that physical pointer basically goes to a big binary bucket somewhere else. So there are var binary, varchar, nvarchar, XML data types, and they sit in this extra little feature set. You can also compress rows. So there's an element of SQL Server knowing that if you want to store a very small value, you don't need a very big integer column to store it in, even though that's how you defined it. So it can do some on-the-fly optimization of the physical storage. It's also then got a much more enhanced compression algorithm which will start to use dictionary compression and start to look for repeating values. So again, while we might only have 80-60 bytes of capacity on that row, compression can actually mean that we can store more than 80-60 bytes of human-readable data on it. So hopefully a bit of insight under the hood when we source that arrow of SQL Server moving data from the MDF file into the data cache, it manages everything as individual 8K pages. So we start to think now about how SQL Server stores its data in a way that influences the performance of us retrieving it. If you just create a table with just a very simple create table statement with a couple of column definitions, it creates them as something known as a heap. And that's basically, there is no physical organization, no indexing. That is just literally a physical dump of row after row in the order that they get added. That can be very fast because there's no metadata to manage and no replacing of data to keep it in order. So that's very good, for example, for data warehousing staging tables, where we want to just load data into a table and then we're going to do something to pull it all out again. For a transactional system that wants to find a very specific row in a very big table, that's the worst situation you could have. So the alternative to a heap is something called a clustered index. And that essentially is a physical ordering of all of the rows in a table according to a specific key. So if my key value is an integer, it will store all the rows in the table in ascending numerical order. That makes it great for SQL Server when it needs to find physically a row based on its value, because it's actually now got a combination of a human readable value that's going to be in a query and a physical location in the table to make finding data more optimum. A clustered index, although it's called an index, it is actually the table. So you can either have a heap or a clustered index, and you can obviously only have one clustered index on a table because it is the table. So most databases will have most tables created with a clustered index because it's a good performance overhead, a good performance benefit. Happy so far? We all on track? Great. So then we come to the magic. Non-clustered indexes, or in common conversation we just drop the non-clustered and we call these our indexes. So for those of you familiar with database design, these are the copies of our columns that are allowing us to do searches based on a much smaller subset of the table, so it's much easier to find specific records based on a certain column. For SQL Server, it does a lot with them, which is why they're so important when it comes to database tuning and query design to make sure it's using the indexes. So we know when we start to think about the parts of a query, we're pretty comfortable. It's going to try and use an index for the where clause. So if we say where month equals December, and we've got an index on December, we're pretty comfortable that that index is going to really help perform to that query because we've indexed the month column. We can then also have SQL Server know that the data in the index is up to date, because indexes are maintained up to date. So if the column that you want to select is in the same index as the column that's in the where clause, it will return the value for your select statement, part of the statement from that index. So it won't just say, tell me the physical locations of all of the rows where month equals December so I can go and get them. It will say, I'll read that index, and while I'm reading that index, I'll read this column that you've asked me to get from the same physical operation. And they're known as covering indexes when we start to pad out extra columns into that index purely to satisfy the select column. If you're doing a join, so join table A with table B, where row ID equals row ID, again, it will use indexes for those join key columns, so it doesn't have to go to the physical table. Again, we want to try and make SQL Server be able to find data as quickly as possible, and that includes during joins. And then finally, in the same way that we can use that as columns in a select query, it can also do some aggregations with the data in the column if we start to put group by clauses in. So what we're starting to see now is that actually one very well defined index could actually satisfy all the operations in quite a complex query, and that stops the database engine having to read this index and go and get a bit of data from here, do a bit more with it and come back here, and another index here. We've got one nice sequential read of that big index where it's doing all of its operations. So hopefully we're all comfortable with that. Hello? Yes.
What about joining multiple tables?
So when you join multiple tables, what SQL Server likes to do is to have an index on the key that you're joining on, because that allows it to make much faster selection of which rows meet the join criteria by being able to use that index. So how does it find data? So the guaranteed, always going to work approach is something called an index scan. So this is where SQL Server will read every row in an index, whether it's the clustered index, which is the table, or whether it's a non-clustered index you've created. It will read every row and ask itself, does that individual row match the condition I'm looking for? Okay, that's going to work because it's like saying, tell me the phone number of somebody, look through the phone book, and you read every person's phone number in the phone book until you find that person because you don't know where in the phone book they are. So it will always work, but it's very rare that that's the best physical operation that you could do. What we like to see, even in data warehouse environments where possible, is SQL Server perform something called an index seek. So this is like having the letters A to Z on our phone book, and where we want to say, I want someone whose name begins with M, we can immediately jump to the M section of the phone book, and we've skipped all of the A to M going through that. So to be able to do an index seek, you have to have the right query, or the query that can use the right indexes, and also the right selectivity. So SQL Server maintains internal metadata about the selectivity maths inside a query. So it may know that actually if there's 20,000 yes values in a column and one no value, it's not going to do much by using that index on a yes column, because 19,999 rows out of 20,000 are all the same. Whereas it knows if I want to find a no value out of those 20,000, there's only one row, so that index is going to get me there straight away without having to do any more work. And this is where query plan optimization comes in, because you might have a great query, but SQL Server isn't choosing to use the indexes that you think it should do. And that's where we have to understand some of the reasons it might not. So which is best? Well, we'll look in a moment as to some of the reasons why non-clustered indexes aren't always great and amazing. In operational transactional systems, our goal is to make every query perform an index seek. When you come to a data warehouse and you've got a multi-terabyte fact table, it's probably always going to do an index scan through those 2 terabytes. And we'll look at some of the reasons why in a moment. So there's always a gotcha. SQL Server 2012, which came out 5 years ago, introduced column-based indexes. So everything I've just told you about SQL Server storing everything as an 8K data page as a row doesn't apply to these. What this does is, as I'm sure some of you may be familiar with, it stores columns rather than rows, and that's great for data warehouses where we've got large numbers of repeating values. So column store indexes, they're not just a way of physically storing data differently, but it also has a different way of executing queries based on the assumption that it's going to be handling large amounts of data. They are now in the Microsoft Data Platform space the default way of storing your data in a data warehouse. They can improve query performance 100 times easily. They can reduce the physical storage pace easily 100 times. The gotcha is that they require large amounts of CPU resource to run, so they can be quite expensive to deploy. But just as an aside, so you don't go away and tell someone tomorrow SQL Server does everything in 8K data pages, we've got this new technology that is becoming more popular. So we mentioned query plans. In SQL Server Management Studio, you can ask it to show you them graphically. So what we can see here is out of this simple select max purchase price from orders, 97% of the effort needed to satisfy that query came from a clustered column store index scan. And then it did a bit of maths here. So what we're able to say is that 97%, that's going to be my first question around optimization. Is there anything I can do to make that an index seek? So rather than having to read those large numbers of rows, it was able to do a much more efficient operation. But that's the type of graphics that SQL Server Management Studio provides, built in for when you want to view it. It looks great with a very simple query. As soon as you come into joins and subqueries, it can become almost unreadable unless you're working with them day in, day out. There's a third-party product. So SQL Sentry or Sentry One, as they now have a free product called Plan Explorer, and that has a much more user-intuitive interpretation of those. So what we might say is, if I've got this query plan, the first thing I want to look at is this red, and then start to look at the orange and yellows, and it allows me to start to then look at which part of the query very easily is responsible for this. So if you do a lot of SQL Server query tuning, this is definitely a great tool, and the very feature-rich version is now completely free. How many of time? 10 minutes? 15 minutes? Okay. So we're all comfortable with how SQL Server works conceptually from what we've spoken. Hopefully some nice, interesting surprises for some. Hopefully lots of new knowledge for those that weren't familiar to start with. But hopefully everyone will take something away from what we've just covered. We then move into the second half of this. How do we make queries run faster? So if you're firing select queries at SQL Server, what can we do to either check that we are running them as quickly as possible, or to help them go a bit faster? So there's a couple of questions. First, why do queries run slowly? And this is really experience-based. And what we start to see is some common themes appearing. So people are familiar with cursors. So these are basically loops that perform operations on individual rows one at a time. SQL Server is designed to work on set-based operations where you run one statement that affects 100,000, millions of rows, rather than a million commands that each update one row. So cursors, great way for hogging CPU. We then start to move into this area of SQL Server either doesn't have an index to help its query run faster, so it's having to do an index scan, which is having to read lots of data from disk, which if we don't have the memory starts to slow down SQL Server. Interestingly then, we start to move into areas where SQL Server might have the index, but we're doing something in our query that can't use those, and we'll look at why in a moment. And actually, you might have the perfectly tuned query, the right indexes, and SQL Server actually ignores them. And we'll look at that again in a moment. And then finally, if you're actually running on a busy transactional system, the reason that most queries freeze, as people describe it, normally comes from locking. When we're running on an analytics environment, the reason that we want to try and not have read-write operations happening, or write operations specifically, is because we don't want this locking contention. So typically, if you ever work in an environment and people say SQL Server hangs or SQL Server pauses, it's because everybody is blocked because of locking contention is generally why, rather than SQL Server just deciding to freeze. So if we have a nice query and we don't have the indexes to support it, we're going to have to be forced to probably do a clustered index scan. So the challenge we've got there is that when we add a non-clustered index, so while they're great for optimizing queries, they actually incur a write penalty on the transactional side of the environment, because every time a row gets updated, every index for that row has to be updated as well. So we generally say for most operational systems, we try to limit ourselves to sort of 4 or 5 indexes per table. So for one write, I'm now doing 5 or 6 writes. For data warehouses, you might have dozens, because we're not doing much updating and we can afford to have that performance impact. And what we can start to see here is some examples of, we've spoken earlier, if SQL Server is missing indexes on those columns in red, it will have to read every row in that table to perform those operations. And if that row is bigger than the amount of memory we've got in the server, we come back to this vicious cycle of ever decreasing performance. So missing indexes tend to be in operational systems the most common causes of bad performance. For data warehouses, we end up with queries typically where we would never be able to predict what indexes we need to have created them in the first place. And that's where column store indexes that I mentioned earlier come in, because they automatically index everything. So that's another reason why they're a bit of a game changer. So we might have indexes there, but SQL Server can't use them. And this is where we move into the era of what's known as non-sargable queries, or non-search argument queryable indexes. And what we're actually doing is we're asking SQL Server to do something with that index that it can't actually operationally perform as nice optimized code. So what I mean by that is, if in my where statement I'm applying a function to the column, SQL Server has to apply that function to every row in the table as it scans through it to see if the answer was 18. So where we put a function in our where clause, we immediately turn our seek into a scan, because it has to apply that function to every row. There are some wildcard searches that can't be indexed. So what we're saying here is find all the event nodes which start with anything but end in the word complaint. You can't index for start with anything. So what SQL Server has to do is to manually go through every row to see if this string is somewhere in that row, and we're not telling it where it might be. So again, it can't perform any mass set-based logic when it looks for that. Bit more of a perhaps surprising one. You can't add maths to what you want to compare. So you can't say, well, your event ID plus 1,000, because it's actually event ID plus 1,000 changes for every row in the table, so it has to calculate that for every row in the table. So again, we're dropping back to an index scan. And then finally, where we start to try and handle nulls with is null and all these not equals, again, you can't index for not equal. You can index for equal to, because you can find a matching row. But you can't say where there isn't a matching row, there isn't a programmatic operation to find not matching rows. You have to find all the matching rows and then exclude them. So again, what you tend to find is that where you have very dev-heavy teams, you will get nice, perfectly tuned indexed database tables, but every big bulky query, especially things where we've got free text search and that sort of thing, drops to a scan and performance really plummets. So last but one slide. SQL Server has something known as the tipping point. And you can Google that term and you can find much more exciting people describe it than me. You might have a perfectly tuned query with all the perfectly tuned indexes, but internally SQL Server knows that there will be a point where it's faster to do a scan of the whole table than it is to navigate all of the indexes to perform an index seek. So typically, when SQL Server knows using its internal statistics that it's going to have to manage or handle more than 30% of the rows in a table, it's no longer quicker for it to navigate all of its B tree indexes. It's faster for it just to do one big sweep of the whole table. And that's a right shocker for some people, because you could have a table which was performing perfectly yesterday with a nice index seek, and then overnight the number of rows in that table have changed, and SQL Server has now decided it's better to do a clustered index scan. We know from how SQL Server works, that's the more efficient way for it to work. It's just slower. And that's a classic example of where we hear this challenge of the query ran quickly yesterday, but now it's massively longer than today. So what we can do is we can actually force it to do a seek rather than scan and tell it, in this scenario, tough luck, we know more than you. And you start to see that in data warehouses. So very simple, select star from table sales facts. It knows it's got to touch every row in the table, so it's just going to physically read from one end to the other and ignore every other optimization it knows about, because ultimately it's got to return data for every row. Likewise, if you use a logical flag in your fact table to say whether or not it's the active record, if most of the records in your table are active, that index, even if there's an index on, is active. It's not going to add much value to it. So it's not going to bother navigating the indexes for is active. It's just going to go through the whole table from start to finish. And what we see there is when we move into those clustered index scan, that's the common data warehouse and analytics query plan behavior, which is a much different world of tuning to our operation environments, where we have lots of non-clustered indexes to try and optimize all the scans into seeks. So any questions on those last few index pieces? I thought, great. So to summarize, in pretty much the time I was hoping to finish in, SQL Server loves memory. We joke that adding more memory is always the answer. You probably will mask issues even if you don't solve them. But as we've seen, if we're handling large amounts of data, even adding more memory will make poor queries run quickly. And I always use this analogy that I just remembered saying that out loud, that SQL Server on modern server hardware now is like a fast car dragging a sack of potatoes. The fast car can make that sack of potatoes actually move really quickly these days because there's so much power to pull it along. But there does become a point where we have to actually tune that sack of potatoes because the car is just, isn't going to be able to pull it any faster than it is. Whether you're running analytics queries or operational systems, indexing, as we've seen for SQL Server, is key. Oracle, I know, has a bit more flex in its performance capabilities to adapt to non-index scenarios, but SQL Server loves them, and every performance tuning guide you will see will help you try and find the right indexes and use them rather than something else first. But I will leave you with sort of this game changer. Column store indexes, if you're new to the SQL Server Data Warehouse platform in 2017, start with them. Ignore everything I've told you about 8K data pages and non-clustered indexes. Column store indexes are a much more efficient way of storing large amounts of fact table data. So my email address at the end, I'm here at the end. If you want me to suggest any further reading, if you want to know how you can learn more about this for career development, or if you think I can help you fix a problem, feel free to email me. Feel free to add me at Twitter at the end that I mentioned.